what if I told you we could generate electricity from, well, nothing more than heat and sound? I'm talking no pistons, no gears, no spinning turbines. Today, we are diving into the wild physics of an engine that literally screams itself into creating power. Yeah, this quote really gets right to the heart of it. I mean, think about everything you associate with an engine. The clatter of metal, the friction, all those moving parts. It's just gone. It honestly feels like something straight out of science fiction, but I promise you, it is very, very real. And that right there is the central mystery we're going to unravel today. It all comes down to this really fascinating dance between thermodynamics and acoustics. So let's just dive right in. Okay, Section 1, an engine that screams. This gets straight to the point. The core idea here is to use heat to create what is essentially a massive contained shout inside a tube, and then figure out how to harvest the energy from that incredibly powerful sound. So here's the high-level summary of how it works. You apply heat. That heat amplifies a sound wave until it's just immensely powerful. Then a little device called a transducer, which kind of acts like a microphone in reverse, converts that intense sound pressure directly into an electrical current. It is such an elegant, solid-state solution to what has always been a really mechanical problem. So how does that amazing conversion actually happen? Let's take a look at the core physics of turning thermal energy into acoustic energy, because this is the real secret sauce behind the whole engine. Now, what's really interesting on this slide is the introduction of this thing called the stack. See, normally, when a sound wave passes through gas, a little parcel of that gas heats up when it's compressed and cools down when it expands. No big deal. But by placing this porous solid, the stack, right in its path, we can control when and where the gas exchanges heat. And that control, well, that's everything. And this right here brilliantly shows how we amplify the sound. By creating a temperature difference across that stack, we force the gas to absorb heat when it's at high pressure and then get rid of that heat when it's at low pressure. So with each and every cycle, the heat does a tiny bit of work on the sound wave, giving it a little push, making it stronger and stronger until it becomes this roaring wave of power. All right, so now that we get the principle, let's look at the actual hardware. What does one of these engines actually look like? You might be surprised by just how simple it is. You know, it all boils down to just 4 main parts. We've already met the stack, that's the heart of it. Then you've got heat exchangers to create that all-important temperature gradient. The resonator is basically the tube that contains the sound. And finally, you have the transducer, turning all that pressure into power. That's pretty much the whole setup. I love this analogy. The resonator isn't just some dumb pipe. It's a carefully tuned instrument. Its length and its shape are specifically designed to make that sound wave resonate, to reinforce itself over and over again, focusing all that acoustic energy into one coherent, powerful force. And when I say powerful, I really, really mean it. The sound wave inside one of these engines can exceed 170 decibels. For context, a jet engine at takeoff is about 140 decibels. This is an immense, even lethal amount of energy, all generated from heat and perfectly contained within that simple tube. Now, harnessing that incredible power isn't a one-size-fits-all kind of problem. Engineers have actually developed 2 main designs over the years, and each one has its own unique way of taming that sound wave. Okay, this slide lays out the 2 main approaches. On the left, you've got the earlier design, the standing wave engine. It's simpler, sure, but the pressure and the gas movement are out of sync, which makes it way less efficient. The real breakthrough is the engine on the right, the traveling wave. By shaping the resonator into a loop, engineers got everything working together perfectly, in phase, which mimics the ultra-efficient Stirling cycle. And that's exactly why it's considered the holy grail of thermoacoustics. So we have this elegant, highly efficient engine, but its biggest advantage isn't just the efficiency, it's what the engine is missing. Let's look at how the complete absence of moving parts is creating a true revolution in how we think about generating power. And this, right here, is the payoff. Without anything grinding or rubbing or wearing out, these engines can run for decades without any maintenance. They're also incredibly clean, using harmless gases and capable of running on any heat source you can find, from the sun to the waste heat pouring out of a factory. This kind of reliability opens up some incredible applications, especially when you realize the whole process can be run in reverse. To understand how, we first just need to know what a cryocooler is. It's essentially a super refrigerator used by folks like NASA to keep sensitive electronics cryogenically cold out in space. And here's the really elegant part. The entire thermoacoustic process is reversible. So instead of using heat to make sound, you can use electricity to create a sound wave, which then acts like a pump to move heat from a cold place to a hot place. NASA is already using this exact technology for zero-maintenance cryocoolers in space.
So the applications are truly game-changing. Just imagine a power source for a deep space probe that can run for 30 years without a single repair, or factories capturing their waste heat to generate their own electricity, or even a solar power system that converts sunlight directly into sound and then into power, with no parts to ever wear out. This is the future this technology makes possible.
Ultimately, this is so much more than just a new type of engine. It's a paradigm shift. For centuries, power has meant motion and complexity. Thermal acoustics offers a future where power is silent, it's solid state, and it's unbelievably reliable. And that brings us to our final thought. In our huge quest for sustainable energy, we often look for these complex, large-scale systems. But maybe, just maybe, one of the most promising answers lies in the elegant physics of a contained, powerful sound wave, a quiet revolution powered by an internal scream.